anonymous, just type away in the comments section. Let's get started. Hello, everyone. Welcome to this episode where we talk about E equals MC squared and what that all means. All right, so let's get started. Now, there's an expectation for you to watch this video already, so I'm just going to move ahead with this video here. Oh, one thing just to check out is your answers. All right. And as for the third question, I do want to point it out because I think a lot of people got the wrong answer for the third question. Okay, so take a look at your multiple choice on the back of course back page 48. And what did you get for question number 3? I think a lot of people ended up choosing not the correct answer. All right, so it should have been 9.0 times 10 to the 13 joules. I have a feeling people got something else that's different from that. Okay, and if you're wondering why is it to the 13, and I think a lot of people got the 16th by accident, remember that we need to measure mass in kilograms. So you need to convert this 1 gram into kilograms. Okay, so once you set your M to be equal to 0.001 kilogram, and then you sub it into the formula, then you'll arrive to the correct answer. So just watch out for that. Okay, so let's get started on our calculations. Okay, first off, what did Einstein state? He said this: mass can transform into energy, and energy can transform back into mass, such that the total mass energy of an isolated system remains the same constant value. And that's the most bizarre thing that Einstein mentioned about. And today we know it's true. We know that if there's any sort of fluctuation in mass, it will convert into energy. But these fluctuations of mass are very, very small. For the most part, they are smaller than the mass of a proton or a mass of a neutron. Okay, so it's a very small value, probably on the mass of an electron, and that's it. Okay, and that's where his formula stems. You're probably familiar with the one which is E equals mc squared, but as you know, here in Canada, we like to be more technical about things and just add a few things to make it grammatically correct. We're looking at the fluctuations in mass. That's why it's delta mc squared as opposed to just mc squared. Okay, so that's just the grammatical add-on that we have here in Canada. If you're an American, then that's why you'll see that the triangle is missing for the most part. It's implied that there's a change. Just like using a stopwatch, right? If you have t is equal to 5 seconds, it is implied that 5 seconds have gone by. But here in Canada, we just like to do delta t, just to be grammatically correct. Okay, the values that will be given to you as constants is the speed of light. You need that. Now, you could use the original value of 299 something 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 458 meters per second. But really, to 3 sig fig, it's sufficient enough. So using this value here, we're okay with that. There's also another conversion ratio. I'll just have you guys write this down in your notes for now, and then we'll talk about how to use that as a shortcut afterwards. Yes, c is the speed of light. Okay, so yeah, you can jot the stuff down up there. But as for what's listed over here, you don't need to copy it down. It can be found on course pack page 49 right at the top. And yes, these are values that will be given to you on any quiz, test, or exam. All right, you're not expected to memorize it. Also, as I've mentioned, if you ended up spending $5 extra on your scientific calculator, it already memorized the mass of a proton, neutron, and electron. And at least in this model over here, these are constants 1, 2, and 3. All right. So some calculators have it built in. You don't need to memorize these numbers whatsoever. One number I do want to point out is, what exactly is this letter U? Okay, and it's a letter that's, often used in chemistry class, and I guess this will be the first time for many of us to see it in physics class. U stands for standard mass atomic unit. Okay, so 1 U is the same meaning as 1 AMU for atomic mass unit. Okay, that's what it stands for. Where did this come from? Well, we take a look at one of the most abundant atoms that we can find here on Earth. We can find in our bodies too, and that's carbon. So you take carbon, a specific isotope of it, one of the most dominant ones is carbon-12. So you take that big carbon-12, and then you share it amongst 12 friends. So you'll cut up the pizza slice, you'll cut it up again, you cut it up, and again, and again, and again, down to the point where you have 1/12 of a carbon-12. That's what 1U is. So you take a carbon-12 atom, you split it up 12 ways, and then you end up getting 1U. 1U is also known as 1 AMU, and the value for an AMU in kilograms is what is listed all the way up there. Is there an expectation for the diagram that I've just drawn for you? Hopefully you know it in the back of your head. I'm not going to test you on it otherwise. It's just knowing that U originally came from a carbon-12, and as the name implies, carbon-12, you'll divide it 12 ways to get your unit of 1U. Okay, so we just needed to have a reference value. We always want to have a reference quantity to start counting from, right? And that's where we got that mass value from. What is the M? Which one is the M, the capital M? Mass of the proton, neutron, and electron? M is mass, atomic mass unit. Hopefully that clarifies that question. Okay, so that's a scribble I usually draw on the side, and most students don't even copy it in their notes. Okay. Okay, so here's the reality, and you've heard about it in the video itself, right? The mass of the individuals is greater than, the mass of the parts is greater than the mass of the atom itself. And it's very strange, right? Why is the mass of the proton, neutron, electron individually greater than the mass of the atom itself? And that's because when they finally bond themselves together, it took energy for that to occur. All right, and that energy for that to occur so that you can have that one stable atom, that's known as the binding energy. So the missing mass is called the binding energy. Some textbooks will also call it the mass defect. Once again, the mass defect is the energy required to hold the nucleus of the atom together. Or in this case over here, it's a breaking. Yeah, this is the breaking version, the binding energy. Okay, so you'll need to have this much energy to break apart the protons and neutrons in the nucleus. Any questions so far?
What does atomic mass have to do with like the energy?
Sorry, you're breaking out. Can you repeat that again?
Well, atomic mass usually binds energy.
I heard mg. We're not worrying about F is equal to mg anymore. I'm not sure if that's your question. You may want to type it out as your signal is spotty. Yep, so feel free to type away at it, and then I'll answer your question. All right. Aside from that, I think there's a bit more to jot down on this slide here. Yeah, the definition of an electron volt. Okay, I'll give you guys a moment to jot it down, and then I'll draw a picture for you to explain what an electron volt is. Okay, good question. All right, here's the weird thing. When you take a mass of any given atom, if you measure all the parts of the protons, neutrons, electrons, it's slightly greater than the actual mass. So in other words, some mass has disappeared. Where did that come from? Now, it's a very small amount. And you'll see in your calculations, that's why we need to carry to 5, 6, 7, maybe even 8 significant figures in our calculation, because we're looking for that minuscule difference in the values. And that minuscule difference is energy that's available for us. Okay, so we can either harness it, or it's the energy, like in this case over here, the energy required to break apart the nucleus. So it's additional energy to just separate it afterwards. All right. Is mass different than energy? Well, again, Einstein stated this, that energy is related to mass, but that's equal to any fluctuations of mass times the speed of light squared. All right, that's what the formula is emphasizing. Energy measured in joules is related to the mass measured in kilograms, but it's related by this constant here. So any small changes in mass will result in big, big changes in energy because c squared is at 3 times 10 to the 8. So once you square it, you're multiplying it by 9 times 10 to the 16. Effectively, you're adding 17 zeros from your mass. Okay, so whatever the mass is, add 17 zeros from it, and that's how much energy there is when you end up annihilating or making that mass completely disappear. So you reduce the mass, energy is released. You gain mass, energy is lost. It is something that was talked about in the video, so I do encourage for you, if you haven't watched the video yet, please do so. All right, it is 21 minutes long, and I want to respect everyone's time here. I am pointing out all the key ideas here of what you need to calculate. All right, so we'll deal with what you need to calculate right now, and then the story behind it. Please watch the video. It summarizes it all. No problem. I'll keep it up, but again, we're going to go through sample calculations. It will show up. Okay, so I do need to talk about what an electron volt is. Can I erase it right now?
Yes.
Okay, just seeing if I have the space here. Okay, so let me just talk about what an electron volt is, the story behind it. Okay, what exactly is EV? Sure, make this as a new note. It's not in my PowerPoint. What is little lowercase ev? What exactly is it? Now, EV is a measurement of energy. And I know that's really weird. By definition, as you copied it down, an electron volt is the amount of energy to move an electron through two metal plates. Okay, so it's plates with different charges. So effectively, you have two plates connected to a battery. Okay, and let's say the battery is set at 1 volt. On the positive end, you'll have a positive plate, let's say on the far right in this example here. And on the negative side, which is where the shorter lead is, you have a negative plate. And you decide to just drop a little electron right over here. Well, as you learned from back in grade 9 science, electrons don't like other electrons. So it's going to hate the negative plate. It's going to quickly run to the far right. And as it runs to the far right, well, it's applying a force and it's traveling a certain distance. And as you know, force times distance gives you work, and that's what an electron volt is. The work required to move an electron between the two plates. If we rewind back, that is a definite definition. Okay, the energy of an electron after it's accelerated through a potential difference of 1 joule per coulomb or 1 volt. Okay, so yeah, let's finish off the definition over here. Okay, 1 electron has a charge of 1.602 times 10 to the negative 19 coulombs. So for those that have already taken chemistry class, you may have heard of this before. There was this famous scientist, and his name was Robert Millikan, and he was the first scientist to discover that, yes, there is a small particle that exists out there surrounding the nucleus, and it does have a numerical value for a charge, and you can't have fractions of it. Okay, so the smallest quantity you can have is that of 1 electron, which has a charge of this number over here. If you had 2 electrons, then you can have a number that's double. 4 times 10 to the negative 19 coulombs. 3e is equal to 4.806 times 10 to the negative 19 coulombs, and etc. Okay, so this is something that was noted about 100 years ago by Robert Millikan. All right, so we're just talking about 1 electron with a known charge as it travels through 1 volt. And that's why they call it an electron volt. Okay, it's literally 1 electron multiplied by 1 volt. And a volt is also equal to a joule per coulomb. In our last unit, I'll tell you that as well. Okay, a volt literally has a separate meaning, it has a double identity. It's measured as a joule per coulomb. So if an electron is measured in coulombs already, so it's 1.602 times 10 to the negative 19 coulombs, and you're multiplying by 1 joule per coulomb, then what do you know? Well, you know that this is equal to 1.602 times 10 to the negative 19 joules. Okay, so an electron volt, it is measured in joules. It's just a very, very small measurement of energy, and sometimes we need to use that. For example, if you're an American, if you're trying to measure really small measurements, would you be measuring it in yards? Would you be measuring in miles? Doesn't seem to make any sense at all, right? If you're trying to measure something rather small, like the thickness of this mark over here, you'd probably measure it in inches. So you could think about an electron volt as the equivalent of measuring something in an inch. It's used for measuring very small measurements. Okay, and then if you're taking larger measurements, you'd measure it in joules, and that will be the equivalent of probably measuring something in yards. It doesn't translate exactly to this, but I hope you get the idea. All right, yeah, if you're talking about very large distances, if you're an American, yeah, you'll be measuring in miles, and we'll talk about this in the last unit. To describe large quantities of energy, we measure it in kilowatt hours. Okay, so kilowatt hours is a measurement of energy. It's just a large scale of it. Joule is a medium scale, and a tiny scale is an electron volt. Okay, so that's the backstory of what an electron volt is, because our calculations will be based upon an electron volt. Okay, so again, that's a backstory. If you want it, if you jotted it down, that's fine. If you didn't, it's okay. Just follow along with the narrative, and you'll be fine. All right, because you won't be tested for that in grade 11, and it will be revisited again one more time in grade 12. Okay, so now that you know that an electron volt is just a measurement of the very small quantity of energy, and that's the backstory behind it. Other questions before we continue? Yes?
So just to make sure, so that capital M in the equation for U is equal to mass?
Oh, no, AMU is an abbreviation. Kind of like, I'm trying to think of a nice clean one. Abbreviation. What's an example? HTTP? I don't know. I can't think of anything nice. HTTP is like Hypertext Transfer Protocol, right? It's just an abbreviation. AMU is for atomic mass unit. It's not a formula. GRASS? Yeah, kind of like GRASS. It's a memory aid.
Okay. No, I mean like the M in front of the EV.
Oh, it's capital M. Is that listed over here? Because that's mega electron volts. Yes. Okay. Sorry, you're talking about this guy over here. M is for million electron volts.
Oh, okay. So that just means million?
Yeah.
Okay.
It's a million. Yeah. Yeah. We'll describe that afterwards. Again, that's a formula which is a shortcut, and we'll apply it when that time comes. The mass of a subatomic particle are different than those of the coarse pack. Which one do we use? They should be the same value. Oh wait, they do fluctuate, don't they? 672-614. Use the one in your course pack. I'm not sure why this one's slightly different. I guess I haven't paid attention to this in a while. Yep. I don't know why there's such a discrepancy. Okay, so use the one from your course pack. I'll double check these numbers afterwards to see which one is the correct one. I don't know why there's such a huge deviation. I mean, I know that in general with these measurements, sometimes in the last two significant figures, the values can change quite a bit, and it's it's different depending upon which scientific community you're seeing it from. Again, it's because of the experiment they did to create those numbers. Okay, and we're trying to get closer and closer to the real value, and it is a challenge. Right? Because as I said, when you're trying to measure things to 6 or 7 significant figures, now you're pushing it to, you're trying to find the distance from your house to the mall, door to door to the nearest millimeter. Right? You're really pushing the extremes when you're hitting, 6, 7, or 8 significant figures. Okay, so let's go through some sample calculations. Right, we'll work through there, and hopefully you'll get the hang of the stuff over here. One of the problems about this lesson here is that none of these things I can prove to you. Okay, I can't do any sort of experiment to show you that this is true. These are things which have been observed in a laboratory setting. And that's the craziest part about a lot of Albert Einstein's predictions. He ended up creating these obscure formulas, and people will just scratch their heads wondering, like, is this even true? How did you even come around to these numbers over here? And, after his death, we're still even proving that whatever he predicted back, almost 100 years ago, it's still valid to this day. And that's the amazing thing about his discoveries. Even though it was all theoretical at that point, his theories did lead to the correct conclusion. Okay. Again, time dilation, it wasn't possible to be measured back then. Today, we use it all the time. Right? If you own a smart device, it's reliant upon time dilation to get the right calculations. Okay. Otherwise, your GPS will never work. Back to the stuff over here, because this is what's relevant. Okay, the mass of helium-4, when you look at it as an entire, it's at 4.00260 U. So here's the thing about this particular topic here. You have to be very specific about the mass, and they will give you it to, 4, 5, or even 6 significant figures. All right, because you're looking for these minuscule changes. So that's what we're trying to look for right now. Okay, what is its mass defect and binding energy? Mass defect, again, is the difference between the mass of its parts versus the mass of its whole. And you're going to see that there's a discrepancy in the numbers. A helium-4 atom, if you recall, is one where there are 2 protons in the nucleus, 2 neutrons in the nucleus, and if it's to be neutral, it needs to have 2 electrons orbiting outside as well. So it's 2, 2, 2. Mass of 2 protons, mass of 2 neutrons, mass of 2 electrons. Again, refer to a lookup table for the mass of the protons, neutrons, and electrons. I'm just trying to see where these numbers come from. It's coming from, it's coming from the U value. Yeah, okay, at least I can trust the U values. So we're using the AMU value of it. All right, so if a mass of a proton is this crazy number over here, a mass of a neutron is this wild number, and a mass of an electron is that number, then mathematically speaking, the value that we have when we hit equals over here, you'd think it'll equal this value here. Funny enough, it's a value that's slightly larger. So when you're looking for the mass defect, you're looking for the differences between these two measurements. Okay, the discrepancy between these two. So you're subtracting the total mass from the mass of the helium itself. I'll go through it one more time right afterwards. How about that? Okay, I'd rather go in a linear flow right now. So we're going to take the 4.03, subtract 4.00 from it, and we end up getting 0.03038. You'll notice that this measurement is measured in U. Okay, so if you want to convert it into kilograms, then you'll need to use another conversion ratio, where 1 U is equal to 1.660539 times 10 to the negative 27 kilograms. Okay, so before you can use in this formula over here, you first have to convert that U into kilograms. Sure, I could show this to you manually of what's going through my mind right now. We know that delta M is equal to 0.03038 U. And we want to multiply it by another fraction, a fraction where U is downstairs and kilograms is upstairs. So when we take that conversion ratio, we're going to place the 1.660539 times 10 to the negative 27 on top. That way the U's will divide each other out.
Wait, why are you multiplying by 1.66?
Again, it's currently measured in U's, but we want to measure it in kilograms. And we know the conversion rate is that 1 U is equal to that many kilograms. Okay?
Okay.
So that's all we're doing. We're just converting U's into kilograms. Question, yes?
Why are you multiplying by 2 in the beginning?
Okay. Okay. If that was a question. Remember I had the picture that's drawn over here. I erased it. That when you take a look at helium, helium has 2 protons, 2 neutrons, and 2 electrons. That's why I chose 2, because that's the definition of what makes a helium. Hope that answers your question.
Oh, sorry, you can go.
That's fine, you can go ahead.
So if we were to get a different, like if it wasn't helium, would we have to multiply by a different number then?
Exactly.
And so based off its like atomic mass and atomic number, we'd know what to multiply by?
Yep.
Okay.
Yeah, that's where it came from. Sorry, I didn't know how far back you wanted me to rewind. Okay, so that was your question. That's fine. Again, I can explain this one more time for those that just need to hear it one more time. Okay. So again, we're just adding up all the masses of the individual parts. Now we want to convert it into kilograms. Now, could you have used this lookup table and measured in kilograms from the get-go? You probably could have, and it would have worked out. Okay, so these values over here, it's just the conversion. By using that conversion ratio of 1.660 times 10 to the negative 27, we converted from AMU to kilograms. That's all it was. Okay. So here, because it's already in U, we need to convert it back into kilograms so that we can use it in Einstein's formula. And yeah, it's going to be a very small value. As I mentioned, we're talking about those little fluctuations in mass. So that's why you need to carry so many significant figures, because those fluctuations in mass results in big changes in energy. So now we can finish off the problem. We figured out the mass, and we just need to multiply it by the speed of light squared. When you calculate this way, don't forget, guys, that you're squaring the 3 times 10 to the 8. So on your calculator, you'll be typing out 5.04472 to the power of negative 29 multiplied by, and if you want to do this for insurance sake, by all means, open up a bracket. 3 to the power of 8, close bracket. That way, you're guaranteed to square 3 times 10 to the 8 as opposed to 3 times 10 to the 8 squared, which is 64. Okay, and you can see the disaster that will cause if you only square just the exponent and not the base. Okay, or if you square just exponent and not the whole term. Okay, it gives you a completely different answer. All right, so if all goes well, you're going to get an answer, and expect the answer to be very tiny, because this is the amount of energy released by 1 atom of helium. So there you have it, 4.54 times 10 to the negative 12 joules. This measurement over here can also be described in electron volts, or millions of electron volts. Okay, so some people are probably wondering, how did I get to this value over here, 28.3 million electron volts? Well, let's go through that whole unit conversion thing one more time. All right, we start off with 4.54 times 10 to the negative 12 joules, and we want to multiply it by some sort of fraction which will get rid of joules and replace it with, first off, electron volts, and then we'll deal with a million afterwards. A constant that will be given to you is that 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. All right, so from our calculations here so far, let's just go through the preliminary part. So 4.54 divided by 1.602, sure, I'll carry some extra, 214 to the power of negative 19. That will give me this number over here. And you can see it's a rather huge number, right? Well, what does that work out to? 28 million. Okay, so if it's 28 million and your measurements are probably only good to 2 to 3 sig fig, why not just call it 28 million? And that's where we get 28 million from. Okay, so yeah, this calculation here initially will give us 2833, what was it? Some crazy number, 337,338. All right, electron volts. Well, since it's such a big number and these numbers over here are all approximated, why not just call it 200? Oh, I put down too many numbers, that's why. Too many threes, I think. Yeah, 28337,338. Okay, why not just call this 28 million electron volts, or if you really want to carry it to 3 sig fig, 28.3 million electron volts. So that's where this measurement here came from. It's from converting it. Is C always the same constant? Yes, it is. Again, there is a proper number for C. I don't remember off the top of my head. Some calculators do memorize it. If you look at the letter C on the calculator. Surprised this one doesn't have it. Usually it's denoted by lowercase c. I doubt that C naught is the answer. I'll try it, but I doubt that's it. Oh, it is. Okay. So this calculator had it memorized that way. 299,792,458. Okay. So that's the official speed of light measured down to the nearest meter. Okay. We'll be using that number? No. You can just write it down as 3 times 10 to the 8 because that's faster than writing down this. And we're only certain of our measurements to roughly around 3 sig fig in these calculations anyways. Okay, so let me explain this question one more time for those that just need a second take on this because it was quite the mouthful. So I'll just rewind back to here again, okay? So the mass of helium-4 numerically worked out to this specific value. So when you look it up on the periodic table, when you take a look at the mass at the bottom, which is the AMU, they will normally just write it down as 4. But to solve these problems here, we can't round to the nearest whole. We need to measure fractions of protons, neutrons, and electrons because those minute differences result in where the energy comes from. Okay, so that's why we're carrying more extra sig fig. So first off, what is the mass of all the parts of helium? I start off by drawing a picture of helium. Helium has 2 protons, and because this is helium-4, in order to have a total mass of 4, it needed to have 2 neutrons as well. So 2 plus 2 will give you 4, and on top of that, this helium has 2 electrons that orbit around it. So we need to add up all these parts together. So that's why the total mass right now of all the parts is 2 times the mass of a proton plus 2 times the mass of a neutron plus 2 times the mass of an electron. We sit down and crunch those numbers, and we find out that we have a value that is slightly more than what we started off with. And yes, this is the weird thing about this mass over here, or this math, all right, that you're going to have discrepancies in numbers. By definition, this discrepancy in numbers is the energy that was lost because you're binding the nucleus together. So now you need to find out the energy required to break apart this nucleus afterwards. Okay, that's what binding energy is. All right, so the mass defect is equal to the total mass of all the parts subtract the mass of the individuals. So when you subtract 4.03 from 4.00, you end up getting 0.03 and a bit of change. Mind you, this is measured in AMU. So if you need to convert it to kilograms, you need to multiply it by a fraction or a ratio where U is on the bottom and kilograms is on top. And that's where that formula comes into play. Okay, so you're going to multiply the 0.03 by that ratio up there. Crunching it through, you'll get a mass of that value. And yes, it's going to be a small value. That small value is what we're going to sub into Einstein's famous equation. Delta M is for the mass defect. Okay, so E technically is equal to the differences in mass or the mass defect times the speed of light squared. And that's when we get to this number here. Okay, so why do we have these 2 standards of measurements? Remember, as I mentioned, when you're measuring distances in American, you're not going to measure, for example, a football field in inches. That's ridiculous, right? Football field, you're more than likely measured in yards. Or if you're trying to measure the distance from here to Vancouver, let's say, you're not going to measure in inches. You're definitely going to measure it in yards. Instead, you'll measure it in miles. So that's the only difference between the value of J and MeV. Okay, they are these 2 different units of quantity, where by definition, 1 EV is equal to this value here. So technically speaking, if you really want to make your own unit conversion, 1 MeV is equal to 1.602. And since we multiply the left by a million, the one on the right we need to multiply by a million as well, or add 6 with 19, which gives us times 10 to the negative 13 joules. That is true. There's nothing wrong with this except that it won't be officially given to you. Okay, so 1 MeV, 1 mega electron volt, is equal to 1.602 times 10 to the negative 13 joules. Okay, so And when scientists look at numbers that are really tiny, like times 10 to negative 12, they scratch their heads because it's hard for us to, first of all, perceive something that small, and it's hard to reference things as well, right? If you're going to measure small distances, why not measure it in inches? And that's the whole idea about MEV, right? MEV is that tiny equivalent, and we often like to have numbers without any scientific notation linked to it. So that's why often with regards to nuclear fission and nuclear fusion, we'll measure it in megaelectron volts because it creates a nice clean number. Can you explain what is happening with the delta MKG? I think it's this part over here. Okay. What we're doing is that we're going to convert this mass, which was originally measured in atomic mass units, and we want to convert it into kilograms. Okay. We know that for every 1 U, it's equal to that many kilograms. So what we're doing is we're multiplying this by 1.660 times 10 to the negative 27 kilograms for every U. That way the U's divide each other out, and you're left with an answer in kilograms. And that's what's happening on the right-hand side. I'm just multiplying the 0.038 by that conversion ratio just so I can have a delta M measured in kilograms, because you need to have it measured in kilograms to use Einstein's formula. Okay, why does mc squared give you energy? Well, let's first take a look at the fundamental units here, right? Mass is measured in kilograms, that's true, and c is the speed of light, measured in meters per second. Well, we're squaring it. In other words, it's in kilograms times meters squared all over seconds squared. Okay, what represents these measurements over here? Well, if you recall, there's another formula that looks very similar to this, which is 1/2 mv squared. All right, we saw that earlier in this unit. And if we just basically look at the units itself, m is mass in kilograms, v squared is speed squared. So we end up getting kg times m squared over s squared. Joules. Joules. That's what energy is. All right. That's the weird thing about what Einstein noticed. He noticed that this correlation is true. And for those of you that are wondering, you know, why does the equation on the right have 1/2, but the one on the left doesn't have 1/2? Because C, isn't C just really V? Yeah, C is really just V, but it's for light. And if you're wondering about the discrepancy of the 1/2, well, remember the 1/2 comes from the fact that you're accelerating an object from rest. So it starts from rest and it ramps up. So when you try to draw a diagram describing the energy or the work underneath this in the force time graph, you will create that of a triangle. And triangles have half. Light, on the other hand, light does not does not speed up. It's either light doesn't move or light does move. Okay, so you end up creating a force distance graph of that of a rectangle. So that's why there's no 1/2. Okay. Light doesn't need to speed up to get to its final speed to have energy. It's either traveling at that speed or not. Okay. And again, this stuff seems rather abstract, rather bizarre. Teaching in grade 11 because the Ministry of Expectations tells us that we need to, and that's why we're covering it here today. I think if there's anything of appreciation, it's just knowing that at some point you're going to get to a branch of physics where you have no idea what's going on, but you have to trust that the math is true. So maybe that's the reason why this is introduced in grade 11, just for you to have that glimpse, that glimmer into just the reality of physics. They'll get to a point where you can't see it anymore. You have to, by faith, trust the math works out. And that's actually the reason why all technology works the way they do. It's not because somebody tried to build it by trial and error. It's because they use the math to design the thing, knowing the limitations are limited by these mathematical equations. That's why your cell phones are as small as they are today. Okay. All right. Any other questions about this question here before I move on? Okay. So that's one question, and now let's move on to the second one. Okay. Whenever you go through nuclear fusion or nuclear fission, you end up getting a mass defect as well. So you're looking at the relationship between the mass after the nuclear reaction and the mass before. All right. So the formula that's on the top right-hand side, it's not an accurate rendition of it. I know I call it reactant and product, and that's just for the purposes of those that have just finished grade 10 science. All right, you probably remembered it this way. Anytime that you have a chemical equation and an arrow afterwards, you have your reactants and you have your product. So whenever you're looking for your mass defect, you're really just subtracting the mass of the byproduct of the nuclear reaction, subtract the parent nuclei. Okay, so it's a mass, pretty much, yeah. Okay, so let's go through this mathematical equation. And I'm going to skip out on B. Don't need to copy down B. For those that are curious about B, it's already available in my PowerPoint, so you can look it up on your own. But I know that about a third of you guys have just finished grade 10 science and moved on to grade 11 physics. So you haven't seen grade 11 chemistry yet. All right, so when it comes to test time, and again, your test won't be tomorrow, but it'll be the day after tomorrow, I think. No, it is tomorrow. Yours will be tomorrow. Day after tomorrow, sorry. Yours will be the day after tomorrow. So, okay. So when your test comes the day after tomorrow, I'm going to give you the test question just like this. So I don't expect you guys to memorize those minute details. So in other words, even though you may see uranium-235 as uranium-235 normally, as I mentioned, you need to carry more significant figures when you're solving these problems. So you're not expected to memorize that uranium-235 is exactly at 235.044. Test is no, not tomorrow, the day after tomorrow. Does it say the schedule for tomorrow? I don't even recall myself. Okay, then it is tomorrow. I should stare at the schedule. Okay, I'll look at the schedule afterwards. This is being recorded live, so let's just focus on these right now. We'll go through the logistics afterwards. Anyone else still need a bit more time jotting this down before I start explaining this? Just a raise of hands. Okay. When you're done, can you just unhand yourself? Unraise hand yourself? All right, so this is one of the many examples with regards to uranium breaking apart. Okay, in the video that you watched, I don't think they used this version here. They used a different one because I'm pretty sure there was 2 neutrons in that example, right? So that's a good question as well. So if you want to have another question to refer to on how to calculate it out, please watch that video. It describes using that example, okay? As I mentioned yesterday, uranium, when you break it, it's not going to shatter exactly in half, right? It's going to shatter somewhere on a very weak line, and you may end up having different quantities of protons in the parts that it breaks up into. So this is one of the many different possibilities. And the question here is finding out how much energy does it release if you break the uranium, and it so happens to break into 1 part barium, 1 part krypton, and 3 neutrons flying about. Any other questions before I get started? That raise of a hand, is that for you need a bit more time? If it is, just keep it up. Oh, okay. All right. Let's get started. Okay, so we got to first figure out the mass defect. We need to look for our delta M. And we know that our mass defect is equal to, and I'll just use the formula up there. You can use it as well. It's not grammatically correct, but it gets the idea across, right? So you want to take a look at what you have before the nuclear reaction. So if you want to call it the reactant, by all means, call it reactant. And then you want to see the products, so the byproducts, after the nuclear decay. Okay, here's where we need to look at this formula and carefully find out the differences between these 2 values here. Okay, we're finding out the mass of what we have in the beginning. So at the beginning, we have a mass of uranium-235 plus the mass of 1 neutron. We're going to subtract it with the mass of barium, 141, plus the mass of krypton, 92, plus 3 times the mass of a neutron. Okay, now let's sub in the values. Again, we don't just use 235. We need to carry as many significant figures as we possibly can because we're looking for those small, minute differences. So 235.044 AMU, often abbreviated down to just the letter U, plus the mass of a neutron, which is at 1.008665. We're going to subtract it with the mass of barium 141, so 140.914 U, plus mass of krypton, which is not at 92, but at 91.926 U. Most common mistake students make is that they forget to multiply the mass of a neutron by 3. Okay, I'm going to do some side calculations. And this side step here, this calculation, you don't need to do it, but I just wanted to show you what is going on logically. Okay, we started off with 236.052665 U of material. At the end, we have slightly less. That's why my delta M, my mass defect, will be a positive answer. So we've lost some of the mass. And the mass that has gone missing became energy that was released. So a lost mass but gained energy to be released into the environment. All right. Uranium is commonly used either in a nuclear power plant or even in a nuclear bomb. So we know that it has a lot of energy harnessed in that one atom. So 140.914 plus 91.926 plus 3 times 1.008665 gives me 235.865995 U. All right, so I'm adding an extra step just so you can see that I started off with more mass and suddenly I've lost the mass. So let's find out the difference between these two values, 236.052665, and that's equal to 0.18667. Just want to cheat to make sure that it worked out to that. Oh, good, it did. Okay, so now we've found the mass defect. As I have this already PowerPointed out, I just wanted to show you the logic in the numbers. That's why I'm writing it out. Can I erase this stuff and put down the PowerPointed version? You have a question or you want me to pause for a bit?
I have a question.
Yep.
Where did you get the exact numbers for the given? Was it off a periodic table?
It will be given to you.
Oh, okay.
Yeah. As I mentioned, all these numbers up here on a test, I'll literally just give you that. Okay, I'll give you the expression and I'll give you the values that correspond to the expression. Now I'll calculate out how much energy is released.
Okay, thank you.
Yeah, no problem. We have to convert from U to kilograms every time. Not every time, and I'll explain why afterwards. Okay, it depends on what the question's asking for. Okay, anyone else still need what's written on the screen here? I'm just making a duplicate. Okay, so it's a duplicate of all the stuff here, and you can see that it gets the same number, at least at that point there. Okay, and I hope that from here you know the process. Okay, the mass defect here is not measured in kilograms, so you need to convert it into kilograms. So you're going to take this measurement over here, our delta M. We're going to multiply it by 1.660539 times 10 to the negative 27 kilograms per U. Okay, and you end up getting 3.09972815 times 10 to the negative 28, I believe. Yeah, it's 28. Okay, I have that power pointed out, so there you go. Mn does not have the unit. Yeah, mass of a neutron has a value of 1.008665 U. Okay, mass of a neutron standard stated in AMU. How would you figure out sig figs? We'll save it for the end. In fact, the truth is you're probably going to get 3 sig fig mainly because you chose that for your C. Most of us use 3.00 times 10 to the 8, and that pretty much limits us. Also, there are inefficiencies in these nuclear fissions, and as a result, the real energy that we get is not exactly the value we calculate out. There's a bit of it lost, but this gives us a decent ballpark figure, and that's all scientists really care about with this. Okay? You're looking at the big ballpark figure, so 2 sig fig is reliable. 3, you're kind of pushing with the 3rd sig fig, but we'll just let it be a 3 sig fig. Okay, so here we have it in kilograms, and now we can use Einstein's famous formula, E equals mc squared. All right, so the energy released in any sort of nuclear fission, like in this example over here, is going to be equal to your mass defect times the speed of light squared. Okay, so it's a very small fractional amount. In fact, this is one thing I wanted to point out. This value over here is going to be less than 1. Okay, is it always going to be less than 1? Sometimes it does breach it, but for the most part, it's going to be less than 1, especially for any question in your homework as well as on the test. So if you get an answer that's more than 1, double check your work because you probably made a mathematical mistake somewhere. Okay. Again, as we mentioned, this whole idea about mass defect, it's something that you won't see if you're just counting protons and neutrons. Okay, so if you count it to the nearest whole, you will not notice this. This formula here, if you round to the nearest whole, will equal to a value of 0. We're looking for those really, really tiny differences, and that's why you're going to have a tiny difference that's less than 1. And that tiny difference translates into the energy that it releases. Okay. Yet once again, when you get your answer here, this is measured in joules. That number over there, it's hard for scientists to see what it is, times to the negative 11. So they'll just often compare it in the inch version of energy, which is mega electron volts. MeV is mega electron volts. It's an electron volt times a million. Once again, to convert this, yeah, I'll go through this. Okay, so we'll write down 2.79 times 10 to the negative 11 joules over 1, just so it's a fraction. We're going to multiply it by, we know that for every 1 joule, that's equal, for every 1 electron volt, it's equal to 1.6022 times 10 to the negative 19. Okay. However, so far, if you go through these calculations, only the joules will cancel out, and we're left with EV. We want it in MeV. Okay. So we need to have another equality. We know that we need to have mega on top. So for every 1 million, it's equal to dividing your answer by that. All right, so go ahead and type that on your calculator. 2.79. Sure, do it up here. Okay, 2.79 to the power of negative 11 divided by 1.6022 to the power of negative 19 divided by 1 followed by 1, 2, 3, 4, 5, 6 zeros, and then that will give us our answer. Where did I go wrong? Something happened here. (2.79 times 10 to the negative 11). Yeah, what happened? Oh, I typed it in wrong. 1.0622. Yeah, that O wreaked havoc. There you go. 1.6022. There you go. Typed it in wrong. That's why. Okay. So yeah, you can convert it into MeV, and this is one way of solving it. But there's another way of solving it. Okay, so before we finish off, let me show you the other way of solving this problem over here. Because this is the thing. Whenever you're solving these problems and you're trying to solve it in MEV, you're doing the same steps over and over again, right? You're taking a number, you're finding a mass defect, that's fine. But you're taking the mass defect and you're multiplying it by this constant. You're taking that constant, you're multiplying by this constant, and you're squaring it. Then you're taking your answer and you're dividing it by this and you're dividing it by that each and every single time. And I want you to try that out. Start off with the number 1. Multiply 1 by this value up here. Then multiply your answer by the speed of light squared. Then take your answer and divide it by this and then divide by that. And if you keep on doing it over and over and over again, you'll notice that you're always getting the same answer. And this is the super shortcut method. Okay. So yes, the formulas will be given to you, including the super shortcut. So if the question is asking you how much energy is emitted in MEV, let's say that was the original question, because you'll see that in your homework, okay? How much energy is released in MEV? There's a quick way of getting to the answer. And here's the shortcuts, okay? 1U is equal to 931.5 MeV over C squared. In other words, C squared is equal to 931.5 MeV over U. And we've seen C squared before. Okay, so here's the super shortcut. We just simply use this number here and we multiply it by here. Let's go through that, okay? So here's the super shortcut. We just simply jump into E equals mc squared, or delta mc squared, which is equal to 0.18667U. Again, this 0.18667U will be multiplied by this number, divided by that, each and every single time to get into MEV. So because it's a very repetitive process, why not just multiply by that what that process is? I think people by accident will square the 931. You don't have to. Remember, C squared is already equal to 931.5. So all you have to do is take 0.18667 and multiply by 931.5. Try it out. Okay, 0.18667 times 931.5, and booyah, we got our answer of 174. Done. Look how much faster that was. Okay, so the approach in solving this problem is totally up to you. Okay, you can take either approach. Gonna wipe out the stuff here. I think I've already shown that shortcut right there. Okay, so that's the super shortcut right there. Aside from that, your homework is course pack 49, numbers 1 through 6. We're not going to solve for B. You can watch the PowerPoint if you want to solve for B. We're not solving for B. Any other last questions before I stop the recording?
Do we have to change it to ME? Wait.
The answer for that is it depends on the question. The question will probably tell you, state your final answer in joules or state your answer in MeV. It's not going to be left ambiguous.
This is calculated nuclear energy release per atom. Found out in
I know this one's ambiguous where it doesn't tell you specifically whether if it's in joules or in MeV. So I left it open-ended here. But that I left it open-ended so that I can cover this, and tell you there's a shortcut if you wanted to go to that. That was the purpose of keeping this open-ended. But you'll see in your homework, it'll be very explicit. State the energy in joules or state the energy in MeV.
Okay, thank you.
You're welcome. Okay, I'll leave it with that then. And let's just end the recording. I'll catch you guys in the next episode.